DCA webinar, DC motor types and usage in typical applications. My name is Carrie Hitchner, and I'm the Marketing Manager for the Motion Control Association. This webinar will be recorded, and a link will be sent to you within the next 24 hours. If you have any questions, please submit them in the questions panel of your webinar screen, and we will answer questions as time permits at the end of the webinar. I'd now like to introduce our presenter for today's webinar, Dr. Urs Kafeder from Maxon Motor. Dr. Kafeder was awarded a physics degree and an MBA from the Federal Institute of Technology in Zurich and a doctorate from UHA Mulhouse in France. He started his career at the ETH solid-state physics department, working on the epitaxy of semiconductor heterostructures, and also attended lectures on general didactics and specialized training for technology education. For more than 15 years, Dr. Kafeder has been responsible for technical training at Maxon Motor. In this function, he has presented many training courses and seminars for the Maxon staff and customers, which resulted in a textbook titled The Selection of High-Precision Microdrives. I'd also like to thank our sponsors of today's webinar. Maxon Precision Motors is a leading supplier of high-precision drives and systems in the USA. Products include small, high-quality brush and brushless DC motors. These advanced motors range in size from 4 millimeters to 90 millimeters and are available up to 500 watts. Maxon combines electric motors, gears, and DC motor controls into high-precision, intelligent drive systems that can be custom-made to fit the specific needs of customer applications. We help provide innovative solutions at competitive prices for a number of applications in various markets, such as industrial automation and robotics, medical technology, security technology, instrumentation, and communications. Our second sponsor is Electromate, and Electromate is the exclusive Canadian distributor for Maxon Motors and specializes in high-performance robotic and mechatronic systems, including servo and stepper motion solutions, positioning actuators, and robots. Electromate's extensive product selection is backed up by just-in-time delivery and stocked inventory. Electromate also offers engineering assistance and technical support by their dedicated customer service team. Now I'd like to hand it over to Urs to begin today's presentation.
Yeah, hello everybody. So I would like to give you today some guidelines for selecting the perfect motor type for your application. For example, which motors are used in the climate control system of a Boeing Dreamliner and for what reasons? Is it a brushed or brushless motor, a flat motor, or elongated one? A winding with slotted iron core or without? How large is torque and speed? And are there gears involved? What are the restrictions on size and weight? And how about ambient temperature? So you see, there's a lot of things that you can consider when selecting a motor. Be aware, however, that there's so many factors in motor selection that usually there's not just one truth. Many motor types and sizes might be appropriate. At the end, it's the application requirements and their relative importance that will point towards a particular motor design. Before we start to answer all these questions, we have a look at the kind of motors we are considering during this webinar. It's all about small DC motors with permanent magnets up to a power of less than 1 horsepower, so let's say 500 watt approximately. And in the following, I'd like to treat these topics. First, some background information about which motor designs are good for high speed or good for high torque. Second, I would like to address the selection of the commutation system. Is this a motor without or with brushes? After that, a few remarks about slotted and slotless designs. And at the end, some guidelines for motor selection according to torque and speed requirements. So let's start with the motor design for high speed or high torque. In a natural and logic way, this will lead us also to the role of gears at the end. We represent the speed and torque capability of motors in a diagram with torque on the horizontal axis and speed on the vertical axis. Here, the axis scale is something like logarithmic, but don't take the axis values as absolute. They should rather give an indication of the order of magnitude of speed and torque. Motors that can run at high speed but rather low torque are typically long and have a rather small diameter. This allows to keep rotor inertia and unbalance low and at the same time the bearing distance large. And both is important for a low noise and low vibration operation. Here we find the standard brushed Maxon motors with one magnetic pole pair and coreless winding. For speeds above 10,000 RPM, brushless motors with a similar electric and magnetic designs are used. Motors with two magnetic pole pairs exhibit a higher torque density, however, at a somewhat lower maximum speed. Now, what are the typical applications for such high-speed motors? Typical high-speed applications are grinders, millers, fans. Here, some example from the medical field. They all use rather long, thin, long types of motors with a long shape and a small diameter. Another example is this blower, which is used in respiratory therapy. So it's to help people breathe, people with lung diseases. The motor needs to be able to speed up very fast to several 10,000 RPM in order to generate the necessary pressure for helping these people to breathe. This is why a brushless, slotless, long, thin, high-speed motor is used. The more magnetic poles we have in a motor, the lower the possible speeds, but the higher the torques in general. Multipole motors are usually made with a slotted winding for more precise magnetic flux confinement. Increasing the diameter with respect to motor length accentuates this design for high torque. So you find here typically the flat motors, often in a slotted design with external magnet. An interesting design variant here is to place the rotor at the inside. The multipole magnet gives a high torque while the rotor inertia is still small. As a result, these motors are extremely dynamic. Typical example for applications that need a relatively high torque at moderate speed are all kinds of pumps. In this example here, a single brushless Maxon flat motor proceeds drives the vane pump of the air cushion. By varying the filling of the air chambers, the passenger can steplessly switch between firm and soft settings. What a nice feeling if you're traveling business class. Another application is pick-and-place applications, and they also need very high dynamics. Here, the parallel mechanism of a delta robot exhibits a very low mass to be moved, and the perfect match for driving are three extremely dynamic ECI 40 motors with internal rotor. The Pocket Delta needs 1/3 of a second for a single pick-and-place cycle, and so therefore it can complete 3 cycles per second. So moving back and forward 3 times in a second. Going back to our diagram, maybe a word about stepper motors. What do you think? Where do they fit into this diagram? Let me answer this question at the end of this section. In real life, however, there are many applications that don't need real high speeds, but rather what they need is high torque. Let's say speeds below 1,000 RPM, but the torques of the order of a few Newton meters. Many manufacturing or humanoid robots work in this range. If we continue the motor design path towards higher torques at even lower speeds and using more and more magnetic poles, we end up with something that could be called multipole direct drive. You can find such motors under the name of torque motors as well. Essentially, also true linear motors could also be placed into this category. The characteristics of direct drives are that they permit a very stiff control because there's no additional mechanics that must be moved, and there's no mechanical backlash and elastic play. Direct drives are very often highly integrated into the application with special designs to fit. There is very little standardization, which results in high costs usually, and particularly high costs if you need very high torques and forces. This is why an alternative is to use standard higher speed motors off the shelf with mechanical transformation elements such as a gearhead. In most cases, the costs are just a fraction of a large direct drive motor. Motor gearhead combinations are standard products of many manufacturers, and you can really get them off the shelf in a proven design and with many variants and options. This is an example where motor gearhead combinations are used. The motor is responsible for controlling the wheels as well as the movement for picking up and putting down the containers. There are many other autonomous vehicle examples with similar setup. A very special kind of mechanics is used in the robot, a robot that mimics the construction of the human body with motors and springs as muscles and ropes as tendons. It's, in my opinion, a nice example to show that mechanics needs not to be a gearhead all the time. So, here we come back to the question about the stepper motors. Stepper motors are characterized by rather low speed and limited dynamics and acceleration properties. So I place them in the lower speed, lower torque corner. Steppers often exhibit a relatively high noise and vibration level, depending on the sophistication of their control. Their advantages lie in the built-in positioning, which makes them interesting for positioning tasks. The lack of time here does not allow to go deeper into the DC stepper motor comparison. So let's stick to the DC motors. And the next question we address in this second chapter is what's the difference between a brushed and a brushless motors? At Maxon, brushless DC motors are called EC motors. EC stands for electronically commutated motors. The most important difference between brushed and brushless motors is service life. Brushed motors suffer from a limited service life of the brushes. Usually you can achieve a few thousand hours, in best cases up to 10,000 hours. In worst case, less than 100 hours. Brush life is difficult to predict and there is no secure way to calculate it. A lot depends on the use. High current, high speed, left-right operation, high vibration reduce service life. All you can do is make some guessing on service life by comparison to similar application and operating conditions. A few thousand hours of service life, however, are sufficient for many applications. Some applications with continuous operation need more service life. They need maybe several 10,000 hours, and the use of brushes should be avoided. In brushless motors, the expected life of the ball bearings essentially limits the service life. Ball bearing life is much better understood than brush life and can be estimated quite accurately. Typically, they're made for several 10,000 hours. But still, keep in mind, there are many applications that really don't need the high service life of a brushless motor. In motorized golf caddies, for example, service life is not really high. Assuming 2 golfing days per week and 1 hour of effective operation per course, you get about 100 hours of operation per year. So there's no need to go brushless. The service life of a high-efficiency brushed motor is perfect. The situation is completely different in this snake arm inspection robot for use in aircraft assembly, nuclear power plants, or the inspection of sewage systems. Operation might be up to 24 hours a day. Accordingly, a brushless motor design with a high service life ceramic gear is used in this case. What are the differences between brushed and brushless motors concerning speed and torque? As a starting point, let's take a brushed DC motor of a given size. In most cases, maximum speeds of DC motors are limited to values below 10,000 RPM. A brushless EC motor of similar size and magnetic design can be operated at much higher speed, reaching 100,000 RPM in some cases. These are perfect motors for applications running at high speeds, such as grinders, cutters, and some blowers. As mentioned before, brushless motors are often made multi-pole with a slotted design. This enhances the torque, but at the cost of speed. Do you have any idea what happens to a brushed motor if operated at these high speeds? Before I answer this question, let me show you a few examples of motors used here as grinders. Grinders, as we know, and drills are typical applications where high speed is important. Here we have an example of an engraving machine using a brushless and slotless motor running at several 10,000 RPM. This hull cleaning robot for ships is a nice example where torque is needed rather than speed. That's why different flat motors are used in the wheels, in the grooming tool, and for the negative pressure attachment device that holds the hull block in place. Coming back to my question, brush motors can also be operated at higher speeds than specified. However, one has to expect a strongly reduced service life due to increased electrical and mechanical wear. The brushes start to vibrate and there's more brush fire, and the motors will be more noisy. However, keep in mind, you will have to look at the specific data sheet of each motor to get the information about maximum speed and torque capabilities of each unit. How about the suitability of motors for special ambient conditions? Brushed motors can cause complication in special ambient conditions. Brush fire is at the origin of electromagnetic noise which might require additional damping. In explosive gas ambient, the sparks might also not be too welcome. However, note that the brushless motor is not explosion-proof by design. Further modification would be necessary. Graphite brushed motors produce graphite dust that might pollute clean rooms or high vacuums or optical devices. And graphite brush needs a little bit of humidity, but not too much, of course, and oxygen in the atmosphere to work properly. Precious metal brushes are lubricated. As a result, both brush types show limited suitability for the use in vacuum applications, for example. Therefore, most motors for special ambient conditions are brushless. Think of motors that can be sterilized, or motors for ultra-high vacuum applications that need previous heating, or motor for space applications, or motor for downhole drilling that have to support high levels of vibration and temperature. Specially adapted heavy-duty brushless motors and gears are used in downhole drilling. They're made to withstand high temperature, high pressure, high vibration, and shocks. With a brushed motor, this would have been impossible to achieve. The robust stainless steel construction makes the heavy-duty motors also well suited in high and ultra-high vacuum application. In particular, they can easily withstand the previous cleaning and high temperature outgassing procedure. And this is an example of a real heavily customized drive. It is based on a long slotless EC motor that needs to be sterilizable. Further adaptations for this implantable system include the selection of biocompatible materials. When it comes to motor operation, let's compare again brushed and brushless design. I always say there's no other motor as simple to operate as a brushed DC motor. All you need is applying a voltage and the motor turns. For operating a brushless DC motor, an additional piece of electronic is needed for the commutation. Cabling is more complex. There are up to 8 connections to be made just for running the motor, compared to the 2 connections for a brushed motor. The situation changes, however, in application with higher level of control. Usually, controllers for motor speed, position, or torque can be used with both types of motors, brushed or brushless. In such cases, the additional costs for the electronics, feedback, and the additional cabling effort are very similar. Concerning ease of operation in system with the speed or position controller, there is not much difference between a solution with or without brushes. Mercedes offers for its E-Class convertible an automatic draft stop that can be activated by the push of a button, this greatly reducing turbulence in the interior. The simple open-loop operation of a brushed motor is fully sufficient for this application. Just apply a voltage to change the draft stop. In addition, the actual service life is very small, a few seconds per activation. Hence, a brushed motor is fully adequate. In this third chapter, I would like to give some insight into slotless windings and slotted windings. In low-power conventional brushed DC motors, the rotor winding is wound around a slotted iron core for magnetic flux concentration and flux enhancement. Maxon DC motors are based on a coreless design. The winding is a hollow cylinder and it does not have an iron core. Similarly, brushless motors can be made in slotted designs. As we have already heard, slotted designs are often made multipole. Brushless motors with a low number of magnetic poles can also be made without iron core for the winding. The same coreless winding type is used as on brushed Maxon DC motors. Now, what makes coreless motors special? Coreless motors have no cogging. There are no soft magnetic teeth to interact with the poles of the permanent magnet. The produced torque is uniform and results in a jerk-free and smooth operation even at low speeds. At higher speeds, the motor excites less vibrations than conventional motors with iron core, hence reducing the audible noise. From a control point of view, there are some advantages as well. The uniform torque is simpler to control and the motor lacks the tendency to stop at the preferred position. Please note, however, that on slotted motors there are different cogging levels depending on the actual design of the magnetic circuits. So you can get smoothly running motors, but also motors with a very pronounced cogging. In surgical robots, smooth and cogging-free motion is essential. Therefore, coreless motors are used. For the haptic feedback and force feedback, use coreless motors with precious metal brushes. Precious metal brushes give a very precise and direct motor reaction, even with the slightest voltage changes. Smooth operation at low speed is required in this telescope. The prime focus instrument package is positioned on a tracking device at the top of the telescope and it is equipped with 24 motion axes, 15 of which are motorized. The movements have to be executed smoothly and with high precision at various speeds, in particular at extremely low speeds. The motors used are coreless EC motors. In addition, for a smooth motion at low speed, it is essential to use sinusoidal commutation. In a slotted design, the iron core permanently changes its magnetization. This consumes energy due to hysteresis and eddy current power losses that grow with the square of the motor speed. By contrast, in a coreless motor, at least for brushed motor, the magnetization is permanently impressed and constant. Hence, there are no iron losses. As a result, the power losses are smaller and the efficiency is higher. Now, what do you think? Why is efficiency so important for handheld tools? Let me give you some hints by looking at two examples. Typical application where high efficiency is required are battery-driven medical power tools. Besides this, the motors need to be autoclavable here, which is best realized with a brushless design. A high power density and efficiency as well as low heating is required in miniature devices such as this insulin pump. And here are some reasons why a handheld tools, a high efficiency might be important. So it's a lower power and current consumption, it's a lower heating, and it's a smaller motor and less weight. The use of high-performance magnetic materials results in a compact motors with high power density. Comparing these two brushed motors of similar length, we recognize the smaller diameter and weight of the coreless designs at the right. Without iron core, the rotor is a hollow cylinder with a considerably lower mass inertia. In combination with the high torque, this results in very dynamic drives with mechanical time constants and acceleration times of a few milliseconds only. At the same time, the rated torque is more than twice as high on the slot than on the slotted design. All this is a consequence of the much stronger magnets that are possible in a coreless design. However, be aware that there are slotted multipole designs with extremely good dynamic behavior as well, and torque per volume as well. For example, the Max and ECI series that we have already seen. This robot named Darwin is used mainly for research and education purposes. The user can easily program the robot according to his own wishes, as the system is based on open source. The very quick and precise movement of the robot are executed by brushed Maxim motors. Each joint is made of a so-called Dynamixel with a slotless DC motor with a high power density. Here, an example of a robot that uses a brushless motor. The important point in these applications is the high power density. It is a lot of torque in a small volume. So, and this leads us to the last section, where I would like to sum up the main motor selection criteria regarding speed and torque. It's just a short summary for the sake of completeness. There is not really enough time to go into all the details. But maybe if you want to see more and learn more, you can also find the Maxim selection videos on the Maxim website. Starting point for motor selection is the motion of the load in the application. So what you need to know is the operating cycles, the speed profiles and friction that you need to move your load, and this gives you the speed and torque requirements that you have to fulfill. In case of mechanical transformation, think of gears and screws and others. The values at the load have to be converted first to the motor output shaft. In our standard diagram with motor speed as a function of torque, this can be represented as points of operation. For example, there can be a constant operation at a given torque and speed, or maintaining a position against some external force at zero speed. Another possibility is speeding up with some mass inertia to overcome. Usually that's where the highest torque occurs. Regarding torque, we condense all the operation points in a few key values. The average, root mean square, load torque, and the extreme operation point, usually at the end of the acceleration, where the maximum load speed and maximum load torque occur. Let me first have a look at speed. We need a motor with a speed limit that is high enough to cover all operating points. The speed limit of maximum motor corresponds to the upper limit of the operating range diagram. However, it is essentially the required torque that defines the motor size. So we have to select a motor with a nominal torque larger than the root mean square average load torque. Short peak loads, as during acceleration, may be located in the short-term operating range, in the white area. The maximum permissible speed of maximum motors can be found in line 23 in the specification section of the motor data. The torque capability of the motor type is given as the nominal torque in line 5 of the motor data. It's a characteristic parameter for a motor type and size. It limits the continuous operating range, that's the red area. A few comments about short-term operation. Higher torques than nominal are possible, but only a limited amount of time. How long an overload situation may last depends on the amount of overload torque and the motor type. As a rule, the larger the motor, the longer the overload can be. Typically, overload can last several seconds as indicated by the thermal time constant of the winding. Roughly speaking, a motor can support 2 to 3 times the nominal torque for periods up to this thermal time constant of the winding. For a given motor type, you usually can choose between different windings. The purpose of the winding selection is to match the available electrical power, it is current and voltage, to the required mechanical output power of the motor, its speed and torque. The different windings of a motor type are listed in columns, the resistance increasing from left to right. The speed constant decreases from left to right. So the first winding needs the lowest voltage to run at a given speed, the last winding on the right needs the highest voltage. The current consumption behaves just in the opposite direction. The left winding requires more current to achieve a certain torque than the winding on the right. Now, for a given application, the objective is to reach all the operating points with the available maximum motor voltage. Usually the most demanding operation occurs at the end of the acceleration. Here, it is the one at maximum speed of 8,000 RPM and maximum torque of 50 milliNewton. All the other operation points can easily be reached by reducing the motor voltage. In this example, we have a 24-volt supply. Mathematically, the winding selection is essentially a matter of finding a speed constant according to the formula on top. Optimally, the selected speed constant should be about 20% higher than the calculated theoretical value. The brown line represents the motor behavior at given voltage. In this case, it lies above all load operating points. This gives us some headroom for proper control and to account for all kinds of tolerances. The brown line can be shifted to lower levels by reducing the motor voltage. That's usually what the controller does. So, I've presented you a lot of information about how to select motors, and let me try to give you a summary here. I'm sorry I have to disappoint all those people who wanted to have something like a flow chart to find the one and only motor and the one and only way to fit into a certain application. Usually, as I mentioned before, there are different possibilities. It's not just a question of the motor alone. but very often of the design concept of the whole device and whole machine that you want to use the motor in. So what I tried to give is some guidelines which motor designs might be a good choice. So I think we can summarize my findings along the general lines of brushed versus brushless motor. For speed and torque capabilities of the motors, refer to the operating ranges and the continuous torque. For high speeds above typically 10,000 RPM, go brushless. Select coreless motors with a low number of magnetic poles. Speeds below 1,000 RPM, consider a gearhead, or go multi-pole and slotted. Concerning service life, the statement is quite clear. Above approximately 3,000 hours of service life, go brushless. Below 3,000 hours, a brushed motor may work as fine. In most cases, brushless motors are better suited or can be adapted more easily for special ambient conditions such as vacuum or sterilization. When it's about smooth operation and precise control, rather use slotless designs without iron core in the winding. These motors also don't exhibit cogging. For simple open loop control, brushed motors might be a lower cost solution. Now, to the end, let me come back to our first example, the climate control system in the Boeing Dreamliner. Analyzing the general requirements in aeronautics, one finds that the motors have to withstand a large temperature range and vibration range, have a lower lifespan, and have to be very, very reliable. All this points towards a brushless design. The particular application here of a valve demands for a rather low speed but considerable torque. In combination with some size and weight restrictions, this results in a multi-pole flat motor with some special gearing. That's it. Thank you for staying with me till the end, and I hope I could give you an insight into different motor designs and their suitability for various tasks. So I will now try to answer your questions on the chart, and I give back to Carrie.
Thanks, Eris. Yes, we do have a few questions to go over. The first is, are high pole count servo motors more difficult to tune than low pole count motors, and do I need special electronics to run multi-pole servo motors?
No, tuning of high pole motors is about the same as with standard motors. At the end, tuning is a question of relative amount of motor torque and load mass inertia in combination with the stiffness of the coupling between motor and load. So tuning and motor behavior and finding good control parameters at the end is a question of looking at the full system, at the full control loop, and yeah. So it's not more difficult, I'd say. And the second part was about if you need special electronics to run multiple servo motors. No, you can run them with exactly the same electronics. It's just that generally the speed of a motor will be lower with multiple motors. But good electronics will compensate for that.
Okay. And the next one is, which motors provide the lowest mechanical time constant, and what are the typical applications for these types of motors?
Yeah, the lowest time constant essentially result in the highest dynamics. So whenever you need very high acceleration, let's say typical applications are pick and place or high dynamic robots in the industrial field. That's where you need this high dynamics and these low time constants. How to achieve this? Dynamic motors, they need to have a low mass inertia in the rotor and at the same time extremely high torque. So you can achieve this is very often high torque means multipole design, and low mass inertia means that the magnet needs to be close to the shaft. So it's the inner rotor design, usually with 2 magnetic pole pairs or more. Is this a good answer? Satisfied?
Yeah, thank you. The next one that we have is I have a subsea ROV application which requires a high MTBF from the motor. What type of motor do you recommend, and how many hours of operation would your motor withstand?
Oh, that's a nice question. That's always the question about how many hours does a motor withstand. Now, if I've understood you right, it's a subsea, so it's an underwater application. And yeah, that's a difficult question without knowing any more details. So what we should know is how deep under the sea level it is, so how high is the pressure, and how is the motor protected from the salt water. So, for example, it could be immersed in oil, so some motors can run in oil. So that would rather be a brushless motor then. So this is really a difficult question without knowing any more details. So that's something for addressing to our sales engineer, and probably they will also have to address our or the R&D department to have a look at the real details of the application and what best can be done.
Okay, no problem. Any other, we're pretty much about out of time today, so any other questions that are submitted will be sent to Urs, and he will follow up with you at the conclusion of the webinar. And I just want to thank everyone for participating today, as well as thank our sponsors once again, Maxon Precision Motors and Electromate. And I just want to remind everyone that this webinar has been recorded, and an email with a link to the recording will be sent to you in the next 24 hours. And then just be sure to visit motioncontrolonline.org for a list of our upcoming webinars. So thank you, everyone, and have a great day. Thanks, Urs.
Goodbye. Goodbye from Switzerland. Have a nice day.